Welcome to this video presentation on heat exchangers. Today we'll be working through example 3, which focuses on determining the heat transfer area and effectiveness of a double pipe heat exchanger. Let's look at the problem statement. In a double pipe heat exchanger, hot water flows at a rate of 5,000 kilograms per hour and is cooled from 95 degrees Celsius to 65 degrees Celsius. Simultaneously, 50,000 kilograms per hour of cooling water enters the heat exchanger at 30 degrees Celsius. The flow conditions ensure that the overall heat transfer coefficient remains constant at 2270 watts per square meter Kelvin. We need to determine the heat transfer area required and the effectiveness. Assuming the two streams are in parallel flow, we will also assume that for both streams, the specific heat capacity, Cp, is 4.2 kilojoules per kilogram Kelvin. Now let's begin with the solution by outlining the given parameters. The mass flow rate, mh dot, is 5,000 kilogram per hour. Its inlet temperature, Th1, is 95 degrees Celsius, and its outlet temperature, Th2, is 65 degrees Celsius. Now the mass flow rate of the cold water, mc dot, is 50,000 kilograms per hour, which converts to 13.89 kilograms per second. Its inlet temperature, Tc1, is 30 degrees Celsius, and the overall heat transfer coefficient, U, is 2270 watts per square meter Kelvin. The specific heat capacity for both hot and cold water, Cph and Cpc, is 4.2 kilojoules per kilogram, or 4,200 joules per kilogram Kelvin. Our first step is to find the outlet temperature of the cold water, Tc2. Now we know that the heat lost by hot water equals the heat gained by the cold water. So the mass flow rate of the hot water times the specific capacity multiplied by the temperature difference for the hot side is equals to mass flow rate of the cold water multiplied by the specific heat capacity and the temperature difference for the cold water. So when we plug in the values and calculate, we find that the outlet temperature for the cold water, Tc2, is equals to 60 degrees. Now the diagram shown here is visually representing the temperature profile for the parallel flow heat exchanger. The hot fluid enters at Th1 and cools down to Th2. The cold fluid enters at Tc1 and heats up to Tc2. You can see that the temperature difference, theta, changes along the length of the heat exchanger, with theta1 at the inlet and theta2 at the outlet. So for a parallel flow, both fluids flow in the same direction and their temperatures tend to approach each other. Now let's calculate the logarithmic mean temperature difference, denoted as theta m. And we are going to use a formula that is provided on the screen. So when we plug in all the values, because we have them, and do the calculation, we find that LMDT is approximately 23.4 degrees Celsius. Next, we use the total heat transfer rate formula, Q, which equals U times A times theta m. We know that Q is also equal to the heat lost by the hot water, so that we can be able to get the area, which we find to be approximately equal to 32.95 square meters. Finally, let's calculate the effectiveness of the heat exchanger denoted by epsilon. Now, effectiveness is defined as the actual heat transfer rate divided by the maximum possible heat transfer rate, so Qmax. So the actual heat transfer rate is given as shown on the screen, and the maximum possible heat transfer occurs if the hot fluid cools down to the inlet temperature of the cold fluid. So Qmax is given as shown on the screen, mH dot Cph, and the temperature difference between the hot water at inlet and the cold water at inlet. So once we put everything together, the effectiveness of the heat exchanger, and we plug in the values, we find that we get effectiveness to be approximately 0.461, and that is our answer. So thanks for watching. If you found this video helpful, please consider subscribing to our channel for more content like this. Don't forget to hit the notification bell so that you don't miss out on our latest uploads.